Welcome back, everybody. And so it's a pleasure to start the afternoon section with Roberto Emparan, who will tell us how proving the quantum regime of near-extremal.
Thank you. Yeah, thank you. Thank you very much for the invitation. I'm enjoying this workshop very much so far. And by the way, maybe you have noticed that I don't have any problem with interruptions for questions during my talk or during other talks. So, so I'm going to be talking about, continuing the subject of this morning, near-extremal black holes and probing quantum, analyzing the quantum regime. This talk is going to be more on, now that we know that black holes close to extremality are dominated by quantum effects, how can we probe this? How can we get extra physics out of this? This is going to be more of a physics-oriented, more than technical or mathematically oriented. I hope that that's fine. It's based on, first on a paper that I put out earlier this year, and it's already published, and also on, I'm going to mention upcoming work with my student Stefano Trecci. This paper should be coming out soon. And what I want to ask and give you an answer to is this question. I think it's an important question. If we have quantum fluctuations in the geometry of space-time, is this something that we can observe? Is there something that we can observe, I mean, without committing suicide and jumping inside a black hole? Is there some way that we can observe and also make predictions for what we should observe? Because this question of observing large quantum fluctuations, this is something that we usually ask in the context of violations of cosmic censorship. If you have a singularity, then there we expect that quantum fluctuations of the geometry should be large. But of course, a singularity is dangerous. If you want to observe it from afar, it should be a naked singularity. And then, the thing is that if it's a singularity, then we don't know the physics that's, in general, we don't know what's the physics controlling that. But as we've seen this morning, there can be regimes where you have a breakdown of semi-classical quantum field theory in correct spacetime, and as I said, this was typically studied in near naked singularities. But what we've learned is that we can also have regimes where you have black holes close enough to extremality, where there are some modes of the geometry that undergo large quantum fluctuations, but the curvature remains small. These regimes are not regimes of Planckian curvatures. Actually, you can have a black hole that's very large, macroscopically large, close to extremality. As we've seen, there's a mode, geometric mode, that has large quantum variance. This is the mode that controls the length of the throat. And this, the curvature here can be as small as you want. Okay? You can take your black hole to be very large, and curvature remains small. There's no Planck scale physics anywhere, but nevertheless, there's a part of the geometry that's undergoing large quantum fluctuations. Okay? In a way that we know how to control without having to use full quantum gravity. We can do it with techniques that don't rely on knowledge of the ultraviolet theory. Now, one thing that many people have been contributing to in this is to show how these quantum fluctuations lead to a drastic reduction in the density of states of the black hole. First people to do this were, or to do this in this context of near-extremal black holes in 4 or more dimensions, were Luca Elieso and Joaquin Turiazi. But of course, we have in this very same room people who have made important contributions, very important contributions to understanding this better and from different perspectives. We have Mukund, we have Chiara, we have Paolo, Giulio, and Alessandro, who have given different perspectives on this problem from different angles, and I think it's something that we can say that it's very well established by now. The idea here is that if you have the density of states in a black hole above the extremal limit, this would be the extremal energy of the black hole, this would be the mass above extremality, so E. This density of states at very high energies, after sufficiently high energies above extremality, what you reproduce is that the density of states is given by the Bekenstein-Hawking area law, the exponential of the entropy. But at energies below some scale, And here I'm going to use the B, so index B to denote a breakdown scale. It could be also the quantum scale. At these scales and these scales above extremality, then you have deviations away from the semi-classical prediction that lead, that render this density of states much smaller than the semi-classical prediction. Okay? And then this has some consequences that have already been begun to be studied. For instance, you have fewer states. A black hole close to extremality has fewer states than the semi-classical calculations would have you believe. And if you have fewer states, if your black hole has fewer states, then you would expect that then this is going to have an effect, for instance, on the emission, on the Hawking emission of the black hole. If you have fewer states, then you would expect to have less radiation coming out of the black hole. Okay? And this has been actually verified. There was a paper late last year where they computed the effect of these quantum effects near extremality on the Hawking emission rate. So you say for this is 1/10 of this energy scale at which quantum effects become important. You see that, well, this would be what Hawking would tell you. And this is what these new, more accurate techniques tell you that what should be the spectrum of radiation. Then you see that there's a strong suppression in the Hawking emission rate. Okay.
So is this statement for non-supersymmetric?
This is for non-supersymmetric. This is so in all this talk, what I'm going to be talking is about non-supersymmetric, not near supersymmetric actually. So we're above, and the ground state is not supersymmetric. Okay. If you have supersymmetry, the story is still very interesting, but it's different in ways that we can also discuss. But yeah, thank you for asking, because that's something that should be clear. Everybody should have clear in their minds. Okay. So thank you.
Is order 1 not so close? The red card becomes essentially the semi-classical one?
So for order 1, it's still smaller, but as the energy above extremality gets much larger than this, then it does become very close. So I mean, you can actually prove analytically that when E is much larger than this energy above extremality, then yeah, you approach the semi-classical prediction perfectly well in the limit. Okay. Yeah, I took this because it's fairly dramatic, that it's much smaller. As I said, this has been studied in many for different kinds of black holes without supersymmetry. As I was saying, the quantum effects near extremality. For charged Rice-Nordstrom black holes, there were these papers. For rotating Kerr and BTC black holes, there's all of these other papers, as I said, involving people here in this room. There's a lesser-known class of black holes, which are hyperbolic black holes, which also have which are neutral, not rotating, but which can nevertheless be near extremality. That I studied in a paper with Javier Magan a couple of years ago. And then near BPS, the kind of the important reference, and there are other later follow-up papers. The important paper is this one, which I won't have much to say about, but of course I'll be happy to discuss if you want to. Now, the question is, so we have these large quantum objects. So these are macroscopic objects that undergo large fluctuations in at least part of their geometry. How can we probe them? Okay. As an external observer. And then, well, before anyone gets excited about the prospects of observing this in astrophysical black holes, let's get a feeling for what are the numbers involved. Because the scale of to which quantum effects become important, so you have, this is the energy above extremality at which quantum effects become important, is, as I told you, is this scale where this is the horizon radius and this is the entropy of the naive entropy of the extremal black hole. Okay. Now this means, let me translate this energy scale above extremality into the wavelength of a quantum of this energy. The wavelength of a quantum of this energy is the size, the order of the size of the black hole multiplied by the entropy. And this is a huge number. Okay? So say that you have an astrophysical black hole that has at least kilometers in size. So then this wavelength here would be kilometers in size. That's already a fairly long wavelength for astrophysical standards. Is way longer than the CMB. So the wavelength of a photon that's coming out, say, of this black hole with this energy of extremality, it would be, to begin with, an energy that would be much smaller than the wavelength of a CMB photon. But it's not only this. This is not the scale that we're talking about. This would be kind of the scale of a quantum of Hawking radiation if the black hole were neutral. But these are not neutral black holes. These are black holes with a temperature which is much smaller. Much smaller by how much? By a factor of the entropy. And the entropy of any astrophysical black holes is 10 to the 80 or larger, if it's just solar mass or stellar mass. Let's not talk about black holes at the center of galaxies. So this number, the wavelength of a quantum of energy that's in the range of this gap scale, or this breakdown scale, is an energy that's easily 10 to the 100, and I don't care what units. It could be Planck units, it could be kilometers, whatever. I mean, this is a huge number, okay? So this is something that for these black holes, certainly for astrophysical black holes, I don't think that we have any chance of observing, because this regime, very close to so close to extremality, is extremely fragile. And that's, maybe if you think about it, it's not surprising. We're talking about a very big, massive object, and we're talking about it being a quantum object. It's not surprising that this is something that's going to be very, very, very fragile. Okay? We don't observe very macroscopic objects, quantum effects easily. Okay? And in this case, the scales are of this order. So for astrophysical prospects, I mean, the question that I was asking, how can an external observer probe this large quantum effect? This I'm asking as a question of principle. Okay? If the nature allows us, or may allow some super advanced civilization, something, to probe these large quantum objects safely from a distance. So it's a question of principle, and then what I'm going to do is thought experiments. I'm not going to come up with any proposal for people at the Event Horizon Telescope or LIGO or whatever. Okay? Yes?
But do I first need to observe the Hawking radiation or the analog of that and then see this deviation, or you have an alternative?
So I have an alternative, okay? So yeah, that's what I'm going to begin with. So first thing is say that you have that black hole, or you want to first to form a black hole that's close enough to extremality, and then to see that it's actually behaving like a quantum object. So first thing that you would do, let's say that you have resources to create a charged black hole. You have lots of charge under your control. You make this charged matter collapse. Then you form a black hole that typically is going to be far from extremality. Then you let the black hole evaporate until it gets close enough to extremality. And then when it's close to extremality, you begin to collect the Hawking radiation, or the deviation, the radiation that it's emitting that differs from Hawking radiation. Okay? That spectrum that I told you, that I showed you, differs from the Hawking prediction. If you can do that, then yes, then you say, well, this is a quantum object. The problem with that is that this is inordinately slow. Okay. First of all, because you have to form the black hole. Let's say that you have godlike powers. You can form, you can collapse charged matter and so on. Then you have to let the black hole evaporate, and Hawking evaporation is slow. That's just to get close to extremality. And then when you're close to extremality, you have to detect the radiation. But radiation in that regime, it's even more suppressed. So then this is a very inefficient, let's put it like that, very inefficient way of observing this object. Okay? So I'm going to propose you something that, at least, well, at the level that we're discussing, is going to be much more efficient way of first creating the black hole and then observing it. Not that, as I said, we're going to be able to do it anytime soon, but it's something that it's much more efficient than this one. The problem with this one is that you're all the time relying on quantum physics, and then the time scales involved here, they all diverge as h bar goes to 0. And for a big object, then this is something that's, at the end of the day, killing us. So instead of relying just solely on quantum physics, I want to do what typically experimentalists do, because we're classical beings, and then we use classical physics in order to probe even quantum regimes. So first, let's form a black hole through collapse, and then form it, try to find it to form a near-extremal black hole from collapse, and then we're going to observe it classically by scattering waves of the black hole. Okay? So relying on classical formation, these are not timescales that are going to diverge as h bar goes to 0, because these are timescales that are governed by classical physics. So the classical formation, collapse, that's something that we've recently learned, thanks to the work of mathematicians, that if you take a charged matter, they did it for charged blast of matter, but in principle it's thinkable that it can be done for other kinds of matter. You collapse charged matter, and then you can fine-tune your collapse so that they could prove that using classical physics all the time, that you can form a classical extremal black hole in finite time. Okay? Of course, there's a problem here. I'm putting this in quotes because we've learned, this is what we've been hearing this morning, that the classical extremal black hole doesn't exist. It's an artifact of the classical limit. The extremal limit is not something that belongs in physics, the classical extremal black hole, because it's dominated by quantum effects. The classical extremal black holes exist in the same sense that the classical hydrogen atom exists. These are things that are not there in physics because they are dominated by quantum effects. So instead, the correct interpretation of what they did is that you can collapse, you can fine-tune your collapse so that you form an object that's close to extremality, but it's not going to be extremal because that's not a thing. What you can form is a black hole in the near-extremal regime of quantum physics. Okay? And you can form it in a classical time scale, which means that we can do it quickly. So this is first. We're buying time here. We can form. We just have to fine-tune it. But then we are experimentalists. Experimentalists, they do fine-tuning for a living. So that's what we ask them to do. You fine-tune your collapse so that you form this classical, or you form this black hole that's very close to the extremal regime. And then that's going to be our large quantum object that we want to observe. Okay. How are we going to observe it? Well, the way that physicists often do this is to send a wave to the black hole. We're going to measure the absorption cross-section, and that's something that's much easier than just waiting for the black hole to evaporate. Not that it won't take a long time also, because the wavelengths to observe this are going to take some time, but it's still quicker than the other process that we talked about before, okay? Than letting it evaporate. So this is what we want to do. And then we want to see whether this can give us some telltale signatures of that the object that we have in front of us is a quantum black hole. Okay. But how do we observe this black hole? How do we send light into it, or send a wave into it? We shouldn't use photons following geodesics for two reasons. Okay, so I'm going to shine a light on the black hole, and then I want to observe it. I want to measure the cross-section, so on. But if I use photons following the geodesics, this is not a good way of doing it. I want to observe it, but not with this. First of all, because these geodesic photons may have too high energy, and they may destroy this long quantum throat. As I told you, that's something that is very fragile. And also, I think that there's a better reason not to do this, and that's that if you throw geodesic photons, then the geodesics, what they are probing is the local geometry of the throat. And I told you that these black holes, the throat of these black holes, is highly fluctuating, but not all of the modes of the geometry have this large quantum variance. It's only the mode that controls the length of the throat. That's the only mode that's fully quantum. Other modes of the geometry, their quantum fluctuations are very much suppressed. Okay, so geodesic photons probe the local geometry, and they are much less dependent on this mouth that's fluctuating. Okay, so if you throw light rays on a quantum black hole, what you're going to get is an image like the ones that you get out of the EHT. Of course, less blurred because you have all these superpowers to produce sharp images, but you're going to produce a classical image, because what you're going to observe is modes of the geometry which are not quantum whose quantum fluctuations are small. So instead of this, what we have to do is to probe the mouth of the throat much more softly. Okay? And for this, what we're going to do is send to the black hole waves of very low frequency. Okay? And the first thing that we did is to study, say, a massless, minimally coupled scalar field. You send this scalar field to the black hole at very low frequencies. Then you want to do it at low frequencies because you don't want to destroy this quantum throat. And then at very low frequencies, the scattering is dominated by the S wave. These are the ones that can penetrate more efficiently. Also, they are going to probe the homogeneous fluctuations. And this mode, the mode that connects the mouth of the throat, that measures the length of the throat, this is a homogeneous mode, something that's spherical symmetric. So then this is what we're going to probe first. And then, well, since we have we're going to do it at very low frequencies, then there will be very small energy absorption, and then the quantum throat will be preserved. So this is, yes?
I missed probably the silly question, but I missed what kind of particle you are thinking of.
A massless scalar field. Then, I mean, do we have them in our universe? Well, maybe there are ultralight scalars out there.
I think.
Yes. So this is just. Then I will say something about photons and gravitons. Okay.
Because you said
no geodesics. Photons, light rays along geodesics. You can have photons of very low frequencies. It could be. So when I was saying photons, I was referring. I mean geodesic. I mean particles with that are not very low frequency. If they follow geodesics, they have higher frequencies. Okay. So, yeah, we're going to do it. And here I'm first considering a scalar field because it's the simplest thing that one can do, and also because it's the most efficient way of S waves are probing the geometry more efficiently. And then we're going to measure the absorption cross-section, and then we want to see whether this absorption cross-section, whether it deviates from the semi-classical result. And it's an old-known result that when you scatter a massless scalar field at very low frequencies, the absorption cross-section is exactly equal to the area. Okay? This is something that you can easily prove in semi-classical physics. Just throw the wave to the black hole, and then this is S wave, so it's probing the black hole of the horizon homogeneously. So then, I mean, maybe it's not surprised that instead of getting, say, the area of the disk, what you're seeing is the black hole as a round object, as a full spherical object. So the absorption cross-section is equal to the area. And this is what we want to compare the quantum calculation to. This is the semi-classical result. We're going to do the full quantum calculation and see what we get. Now, this semi-classical result, that the absorption cross-section is equal to the area, then, well, we may think that this is this absorption cross-section may also be giving us a measure of the number of states that can absorb the radiation. Because we know that the area is a measure of the number of states of the black hole. So, I mean, as I said, the number of states is A/4 exponentiated. That's the density of states of the black hole. So you could say that the absorption cross-section can be a phenomenological way of probing or measuring the number of absorbing states that the black hole has. And this is the semi-classical regime. Okay? So then, what can we expect in the quantum regime? I told you that the density of states of the black hole is reduced in this quantum regime because quantum fluctuations make the density of states much smaller than the semi-classical value. Okay? So then, what you might expect, and this is what I was actually expecting before doing the calculation, is that when I do the calculation in the quantum regime, since the density of states is much smaller, then, and there are fewer states that can absorb radiation, I would expect that the absorption cross-section in the quantum regime should be much smaller than the area. Yes?
So for the classical result that sigma is A,
yes.
Does it not depend on whether it's charged or not?
No. What the wave has to be is neutral with respect to the black hole. If the wave has charge, then it may depend on the black hole. But if you consider, say, a massless scalar field in any spherical black hole geometry, and then you don't consider any back reaction, and you're taking the limit where it's just a wave propagating in some semi-classical geometry, and it's a wave that doesn't couple to the geometry in any other way than just a minimal neutral coupling, then the result is universal. If the wave has charge, then yeah, then it's more complicated. But a minimal scalar wave in any spherical symmetric geometry, that's the result. Okay. You probe other things, yeah, and that can be interesting. You can use different probes, and then later we're going to use different probes. Well, this was the expectation, that the absorption cross-section in the quantum regime should be smaller, but that's not the result that I found when I did the calculation. Even if the density of the states is smaller, what I found is that the absorption cross-section was larger than the area, and then, well, the area, as I'm saying, is larger than the density of states. And then this is larger and larger even as you get closer to extremality. So this was something that at first looked counterintuitive when doing the calculation. Now, what is the explanation? I'm giving you first an explanation of the kind of a summary, introduction summary of the talk. Then I will give you more of the details of how this comes about. But how can the absorption cross-section be larger than the area, than the symmetrical result, even if we have fewer black hole states that can absorb the radiation? Well, the reason is that the quantum effects, even if you have fewer states, they are more efficient at absorbing, because the quantum effects enhance the transitions between individual states, okay, relative to the semiclassical value. And this is something for those of you who have been following developments in recent times about controlling quantum effects, or say measuring the two-point correlation function in the presence of a black hole in the quantum regime. Well, one of the things that we've learned is that the latent correlations, the two-point function, are enhanced in a quantum black hole. Typically, when two-point correlation functions in the presence of a black hole, they decay exponentially. It was normal ringing, a little bit like that, but that's, it's not exactly quasi-normal ringing, but it's closely related. But the latent correlations in the presence of a black hole, they decay exponentially. But if you take into account these quantum effects, the quantum effects that I'm going to be including, then this latent correlations, instead of being exponentially suppressed, they are just power law suppressed. I'm not talking about what happens at very late times, like the ramp and the plateau. Those are different effects, but they appear at exponentially late times that I'm not including. So we have longer correlations at late times, larger correlations at late times, then this means that you have larger transitions at low frequencies, larger transition probabilities at low frequencies. And this is what's driving this or enhancing this transition between individual states. Okay? And this is something that overcomes the suppression in the number of states. You have fewer states, but they are more efficient at absorbing radiation. Now, there's another thing that we've also done. So after studying scalar fields, this is what is in the paper that's going to come out with my student, Stefano, that we found that near-extremal black holes, they become transparent to electromagnetic and gravitational radiation below some frequency threshold. And this is something that may sound surprising, because if black holes are anything, it's precisely that they are not transparent. Okay? They absorb radiation. So how come do we have black holes becoming transparent in this quantum regime? And the reason is fairly simple to understand. We're in a regime where we have to take into account quantum physics, and in particular the quantum physics that the angular momentum of the black hole is quantized. So we begin with a black hole that's not rotating. Then we give it a unit of angular momentum, so the black hole is going to be excited above some energy. It's going to acquire some energy because this angular momentum is giving it some rotational energy. But the rotational energy is quantized. It's quantized by this number. Okay, so then from the black hole in the massless or in the massive spinless state to the first excited spinning state, there's a gap. Okay, and then this gap, if you want to overcome it, then you need to have enough energy. So if you throw a photon, a photon or a graviton will have some angular momentum. Okay, so they will absorb, they will make the black hole jump from spinless to spin 1 or spin 2. If the black hole absorbs a photon, it has to have enough energy to reach this energy level. So the fact that the black hole energy levels or the black hole levels for rotational energy levels are quantized, they mean that if you're throwing radiation at the black hole with a frequency below this threshold, then the black hole won't be able to absorb it. That's just standard quantum mechanics. Okay? So the black hole will be transparent to photons and to gravitons and to any spinning waves. Also, if you want scalar field, spin, higher spin.
Go down like a power down
Yeah.
with frequency.
So see?
I'm asking if I did the same computation classically.
Classically, yeah. I mean, there's yes,
Zero
yes,
like a
yes,
power
yes. It's a power law. That's right. Yeah. But here, yeah, and then if I'll get there, I will show you the. I mean, this it goes to zero at below some threshold. Yeah, but the classical result is non-zero, and actually much larger than even in the regime where you are above this threshold. It's still very much suppressed in the quantum regime. Sure.
In the scalar case, when you say you get a larger
Yes.
absorption, does that depend on the frequency of the
Yes.
scalar wave?
Yes, but
There's some asymptotic value which is fine.
yeah. So I mean, it's always larger the quantum absorption cross section for the massless scalar field. At the high frequencies, it tends to the same value as in the semi-classical case.
But in omega to zero,
In the omega goes to zero. As omega goes to zero, the absorption cross-section goes to a finite value. If you're, say, finitely away, I mean, the black hole has some finite energy above extremality, then as you go to omega goes to zero, it tends to a finite asymptotic value. At least, well, to the precision, as I said, I cannot deal with frequencies which are exponentially small in the entropy. I can deal with frequencies which are power law in the entropy, but not exponentially small. Those would correspond to having control over extremely long times, exponentially long times in the correlation function. And that's something that we don't know how to do. You would need ultraviolet physics, presumably. Yes?
Transitioning from, say, observing 1, 3, 1, 4 into graviton, is that matrix element larger than the matrix element without including the
You mean for a spin? In the case with spin? Yeah. Yes. I think, yeah, in general, I think it's larger. It depends a little bit on details, but in general, I think it's larger. But then it's suppressed by having much fewer states. But I think in general, I mean, the matrix element, I mean, the matrix element, the transition probability for individual states, it's larger. Yes. 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 So that may depend. So you want to send I mean, a kind of a not a monochromatic wave. Then in this case, it may depend on the details on how you do it. But I mean, the suppression is very large. The suppression is very strong. There are thresholds where one effect dominates over the other. So the answer to your question will depend on. I think that you can probably cook up regimes where you have one of them dominating or the other.
But this effect should therefore also be visible in scalar. So you just scalar.
Yes.
Yeah.
So so I was talking just about S waves, but the first thing that we computed were higher partial waves, and very similar effects have happened. Yes. So if you send a wave, say a plane wave, then you're going to have all of them, and then So this will depend on the details of your experimental setup. Okay. So that was kind of a summary of the talk. I don't know how I'm doing with time. Yeah, still have time. Yeah. So, but if you have any questions before I go to more details, I'll be happy to take them. So first, I'm going to begin with, I mean, we already had a review of these effects. So Chiara and Mukund were talking about these things. In particular, Chiara told you that, well, we've learned that, we've known for some time already that close to extremality, there was something funny about black holes, in particular about their thermodynamics, because you don't have any, you're so close to extremality so at a temperature so small that you have very little energy available even to emit a single quantum. And what this meant is that semi-classical thermodynamics breaks down. And what this meant, in particular, is that the semi-classical or quantum field theory in curved spacetime also breaks down. Of course, when this thing happens, when quantum field theory in curved spacetime breaks down, we have to go to quantum gravity. And that's where we usually throw our hands up. But in this case, we don't have to, because in this case, we can have control over that. It's not that we need full quantum gravity, but at least we need some control, quantum gravitational control at low temperatures. That quantum effects are important at low temperatures, that's something that's not a surprise. Go to any lab where they're doing low temperature physics, they will tell you that, well, of course, close to the ground state, I need to take into account quantum physics. What's surprising is that this quantum physics, in this case, in the case of black holes, is one that we can control. Okay? Now, this is, you've seen pictures like this morning in Kier's talk. One way of doing this analysis was by going to the throat of the near-extremal black hole, performing a closed line reduction, decoupling it, and then obtaining a one-dimensional effective theory for the mode that dominates at these low frequencies. Nowadays, we know of other methods where we don't have to go to the throat. We can keep all of the geometry. So we have Paolo, Giulio, and Alessandro. Also, Mukund has done work on this. How we need not do this, that there are ways where we can keep a perspective of all of the space-time. But this was the way that it was initially done, coming from developments about JT gravity and the Schwarzenegger theory at the boundary. So that's the picture that I'm going to be using. Okay, so we have this throat that has this mode that controls the coupling of the throat to the asymptotically flatter region. It's what we call the Schwarzian mode, the Schwarzian geometry, which is classical mechanics or quantum mechanical theory. It's a theory of just one dimension. And that's the one that controls, as I say, how this mode fluctuates. Okay. And the thing is that this, well, there was some talk about this morning. In this case, in this regime, this is something that can be exactly quantized. The results that you obtain are one loop exact. Okay. In other cases, we don't have that much control, but in this case, at least in this strict limit, in this strict case, it's one loop exact. Now, what you can do is compute the one loop determinant of fluctuations. We heard about all this also this morning, and then you get the famous T over 3/2. Okay. Which is something that measures the quantum fluctuations of the throat, and you see that this effect becomes large when the temperature is sufficiently small, which means that you can have these large quantum fluctuations here. This is then, if you go from the partition function to the density of states, this reproduces the same plot that I showed you earlier. So, well, any questions about this? I went over this fast because we've already heard about this morning, but if you have any questions, then I'm going to change and go to the study of the absorption cross-section. Now, let me mention also that at the same time that I put out my paper, there was also work by Anna Biggs doing very similar analysis. Now, this is what we want to do. We have this quantum object that we know how to describe. We know how to describe the quantum levels of the black hole. Okay. Now we want to send a wave into the near-extremal black hole. We're going to parameterize the black hole by first the energy. This is the energy at which quantum effects become important, and this is the energy above extremality. And we want this quantity to be of the same order as this one. Okay. Now we send a classical wave with large occupation number, and we send it at low enough frequencies. They should be at least this low, and we're going to go to even the regime of interest to us is regime frequencies which are even smaller than this. Now, how do we do this? So we set up a wave at a large distance from the black hole. We send it into the black hole. It propagates away from the throat like a semi-classical wave, but then it gets close to the mouth of the throat, and there we use, well, at least the intuition that we gain from ADS-EFT. Here we have an ADS throat. This wave, when it comes to this region, to near the ADS2 throat, then, well, we can decompose it, we can match it to some solution of the wave equation in this region. We take the component that's large near the mouth of the throat, and then we take this to be a source for a response operator in the throat. Okay, so this is the total action of our system. The black hole reduces to this Schwarzian action, and the wave equation reduces to, well, some source coupled to some operator that characterizes, as I say, how the throat of the black hole is responding to this external perturbation. Okay, and here this is characterized by a conformal weight, which depends on the type of wave and spin that we have. So at the end of the day, the picture of what I'm doing is the following. We're replacing, so we have the field outside the throat is propagating as a classical field. But when it gets close to this throat, then we're replacing this classical throat, we're replacing with what we think it's the right description. This is not a classical throat anymore. This is a quantum state. And then instead of using the geometry here, what we're using is this Schwarzian theory that we know how to describe, we know how to quantize, we know the energy levels of this quantum theory over here. So this is a state on this Schwarzian theory. So instead of using the geometry of the throat, we take a quantum, an energy eigenstate of the quantum black hole. Okay? And instead of considering the propagation, classical propagation in this geometry, I'm going to study this coupling between the source here at the boundary and the response at the throat. Okay? So this is how we do everything. We want to probe this object, and then we replace the classical throat with the quantum Schwarzian theory. And then, well, so we're sending a wave that's oscillating. So we're sending a wave, and then we have the quantum throat. How does the system respond? Well, you have the quantum throat, you're shaking it at a periodic rate, and then as you shake your quantum black hole at this periodic rate, it will get excited. Okay? So then this periodic source at the boundary of the throat is going to excite the black hole, and it's going to induce transitions between black hole states. The black hole states can absorb the wave, or there can also be emission, stimulated emission. Okay? So we're going to have both effects here induced by this fluctuating source, oscillating source at the boundary. How do we compute these transition rates between states? Well, we just use the rules that Senor Fermi taught us. We have transition states from initial to final states. They are given by this transition element multiplied by the density of final states. Okay? And then we can have both absorption and emission. Here we have a factor that we get from matching the propagation of the wave from infinity down to the throat. That's something that is telling us what kind of, what's the strength of the source that's exciting our system. And then I'm going to also neglect spontaneous emission because I'm doing this semi-classical analysis, this semi-classical experiment. So then I can use the Fermi rules to compute the absorption rate and the emission rate. Just, as I said, it's something that follows from Fermi. And then the total absorption rate per mode is going to be, so that you can have emission, but you can also have stimulated, you can have absorption, but also stimulated emission. So the total absorption is absorption minus stimulated emission. Okay? So this, all of this is just the conventional quantum mechanics as you teach your undergrads. And then I use essentially the optical theorem to go from the absorption rates to absorption cross-section. So then, well, the final result in principle is this. This is the formal expression that I have. If I can compute these quantities for my quantum black hole, then this is the results. Okay, so what I need is that the quantum theory of my black hole gives me the density of states and the transition rates between different black hole states induced by this operator that tells us what is the response to the external field. So the source theory gives me these two quantities. So it gives me, this is the density of states that I told you about, and the two-point function is something that was computed a few years ago. It takes this form.
Sorry,
Yes.
what was
So this is the operator that's dual to a massless scalar field in the throat. So I have an ADS2 throat. That in ADS-CFT in general, you have some scalar field in the throat that's dual to some operator in the boundary theory. So that's this operator. In this case, for a massless scalar field, this is going to be a conformal primary of the dimension 1.
And that's the only thing you need to know.
Yes, exactly. I don't need anything else. If I have a field of other spin of other properties, then I have to use a different operator with different conformal dimension, but all of these things have been computed. So it's very simple. And actually, this is the simplest two-point function that you can study in the Schwarzian theory. So it's something that's explicitly known. It's the operator, as I said, that's dual to the massless scalar field. So then this is the final result. Okay, so this is something that comes out of these these factors that I had over here. I mean, had the factors of r plus square and everything. So this is the final result. This is the absorption cross section of a wave of frequency omega on a black hole that has energy EEI above extremality. And first, as a sanity check, one can the first calculation that I did is take this and take the limit where the black hole is farther away from this quantum regime, so it should behave semi-classically. Then if you take this regime, where the black hole is at energies much larger than these other scales, you recover the semi-classical result that the absorption cross-section is equal to the A. Okay, so everything fine. I recover correctly the semi-classical result, but then what I'm interested in is going to the regime where the black hole is actually behaving as a quantum object. And then, well, this is an expression that's a little complicated, but you can easily plot. And then I plotted it, and then I saw, wow, I mean, it's coming out larger. So the absorption cross-section is larger.
That order of approximation, yeah, first order theory is exact, except that at certain point you take a little bit of n plus 1 equals 1.
Yeah. So that's because I'm neglecting spontaneous emission. Yes.
Okay.
That's fine. Yeah, that's not a, yes.
So the matrix element in G gravity, doesn't it take the form as product of gamma functions?
Yes.
So
this the gamma functions for this operator, they collapse to this.
So you choose a specific value for the
So if I take this to be, so it's a gamma functions where there's delta. When delta equals 1, everything becomes much simpler. So it's the product of these 4 different gamma functions, which, so if you want to do other things, then you're going to have all of the gamma functions and everything is going to be more complicated. But in this case, yeah, it simplifies nicely. Yeah, but you're completely right. Yes. Yes.
So the first term diverges when I send omega to 0.
Yes, but I mean, so when you send omega to 0, this seems like it diverges, but when you take into account all of the, I mean, also the other contributions, it comes out finite. Yes, that's, yeah. So, I mean, there's a cancellation. That's something that, yes. No, the numerator here, yeah, I mean, it's safe, yes. But the result is this, something like this. So this is the absorption cross-section compared to the area, as I plotted it as for frequency fixed in units of the black hole energy. So this is for black holes that go away from extremality, go closer to extremality. This is farther away from extremality. This is the regime where you should recover the semi-classical result, that they are equal. And then you see that they are larger. There's a kink here because, well, for high energies, you can't have stimulated emission because you don't have enough energy to emit. But you see that this is larger. Okay? And this is, well, the result when I first plotted it, I wanted to explain. And that's, as I said, and this is the fact that the absorption cross-section is larger. What this means is that the density of states is underestimating the absorption near extremality. So it's not just density of states that tells you whether you should expect larger or smaller absorption cross-section. You have to also take into account, as I was explaining before, what is the efficiency of the individual states for absorbing radiation. And that's what you can see in these plots. if you find these are the absorption transitions, these are the matrix elements. When you strip of the density of states, you see that these matrix elements, they are larger in the quantum regime. The density of states is smaller, but when you multiply them, when you take the two of them in together, then you see that the quantum absorption rates are larger than the semi-classical absorption rates. So this effect, that this is larger, that the states are more efficient at absorbing energy, this is something that overcomes the suppression that comes from having fewer states. Okay. So, I mean, the result is that the black hole in the quantum regime looks larger. It has a larger absorption cross-section. Okay, and that's kind of a, this even looks larger, it's larger font. Okay, so that's a clean phenomenological signature of having a quantum black hole instead of a classical black hole. Then we also wanted to see, next thing that we did is study the absorption not of a massless scalar fields, but of, well, the fields, radiation fields that are actually in our universe, photons and gravitons, which carry spin. And then, as I was explaining before, here you have this is the density of states that you have for a spinless black hole. It's this one that we've seen before. But if you have if the black hole has a spin, there's this gap over here caused by the rotational energy. And then if the frequency, so if you have if you send a wave of some frequency into this black hole and say that the frequency is over here and the black hole is over here, then if the black hole has to jump, or the frequency of the radiation is such that it would make the black hole jump into an energy in this range, then, well, there's no black hole here, there's no absorption, so the black hole cannot absorb. It's transparent. Okay, so that's a fairly simple, again, physical prediction. And then if you want the actual plots, I mean, this looks, it's not coincidental that it looks like this, because it's dominated precisely by the density of states. This is the result of the actual calculation. The previous one was a cartoon. So if you plot the absorption cross-section for a photon, and n equals 1 photon, then you plot it as a function of the frequency, then, well, it's 0 until you reach the threshold at which you can begin to absorb radiation. If you ask me, well, can I plot, like before I had the plots of the semi-classical and the quantum absorptions together in the plot. Here, the semi-classical absorption cross-section would be much higher. So even if here the black hole is not transparent, it's very, very, very faint. Okay, and it's absorbing very, very little radiation. It's only much later when the black hole begins to be visible. Okay. So these are, I mean, the main results that we have. Let me say something about this result. We've done it for a 4-dimensional charge Rice-Nostrom black hole. You can also consider what happens for other black holes and other dimensions. The result is very universal, at least for static black holes, as long as your black hole has the near horizon, near-extremal regime is dominated by the Schwarzian, which will happen at least when the sector, gravitational sector is dense and Hilbert, probably in other cases as well. Then the result is still valid. All of the things that the spin transparency, as you've seen, is also a very simple thing. It's just that the fact that spin energy is quantized, because spin is quantized. So all of this is very, very general and very universal. Okay, and then getting the results is just a matter of changing a few numbers over here. For rotating black holes, for Kerr black holes, it's going to be more complicated, like everything with Kerr, but still these effects should be there. Let me skip this. Yeah. What else can we do? We've been probing black holes. I'm saying that we can send waves to the black hole, but then we can also probe black holes with static probes. There's this tidal deformability of black holes, which gives rise to this thing called the love numbers. And then, well, the fact that they are called love numbers gives rise to all sorts of corny puns. And I'm not immune to that, so we're preparing a paper on quantum love, where we're analyzing what are the quantum corrections to love numbers for these black holes. This is in progress with these people. Then, well, there was this question about, well, what happens when instead of being near non-BPS, you're near BPS. Then things change a lot. You can also have a transparency, and then you can also have other effects, but in general the physics is different, and that's something that would be, it's been analyzed already in these papers more recently, but I'm not going to say too much about it. It's also very interesting because they put the emission and absorption for these black holes give also very distinctive signatures, different spectral lines and so on. So I will come now to the end of my talk. I began the talk asking this question: can we observe large quantum fluctuations of the geometry? And well, my answer in this talk is that yes, and that the two of the telltale signs of the quantum, of having a quantum black hole in front of us, is that if we scatter waves of it, then at very low frequencies for scalar fields we would see enhanced cross sections. The black hole would look larger, but if we throw photons and gravitons to the black hole at low enough frequencies, then the black hole would be transparent to them. Okay, and then, well, with this I will stop and thank you. Yes. It's I think it's the square root. I mean, at the low end of energies is the square root of the E breakdown over the energy above extremality. If you fix the, I mean, that, yeah. Yeah, yes. That's in that limit. In general, I mean, the expression is a little more complicated, but in that limit it simplifies. And I think it's a square root. I mean, it's some power, and I think it's 1/2 of the ratio of the breakdown energy to the energy above extremality. It can be quite large. I mean, that's something that I found surprising.
Yeah, this is not a regime where typically you have control from unitarity bounds.
No.
But you might wonder whether there is this parametric enhancement means something that there might be corresponding separation somewhere else.
Yeah.
For the black hole or
yeah, that's something that yeah, I haven't explored, but it's true. Yeah, I mean, there's no, I mean, input. At some point, yeah, you're going to hit unitarity bounds. Well, clearly. Yeah.
I mean, that might mean what you said about inclusive processing. You don't try to
yes. Yes. Yeah, that's something that yeah, I haven't explored, but I think yeah, I mean, there should be such bounds. Yes. There's one question over here.
In the classical case, I imagine if I want to we get some absorption, which was area.
Yes.
If I want to receive everything that reflects, I have to wait for some long time.
Yes.
Is it? Can I translate your result
yes.
into some kind of cutoff in the time that I
yeah. So yeah, you need a time that's again, it's on the order of the wavelength of the quanta that you're scattering, right? I mean, if you want to observe this, then you have to. Yeah, so that's a very long time. Is that your question? I mean, what's the time scale for observing this?
Yes, I want to see if I can Is it, for instance, I want to understand if it's related to this typical time scales that appear in for near-extremal black holes, like e to the s.
It's not e to the s; it's a power. Yeah, I mean it's actually linear. Yeah, it's linear in the entropy. So it's not exponential. For exponential times, you would need, if you wanted to see the very, very, very fine structure, I mean the discrete structure of levels. I mean, here we can see, I mean, the continuous spectrum. Well, there's this gap, which is also good. But then at the fundamental level, the spectrum should be discrete. And observing this discrete spectrum, that's exponentially long times.
If I want to see the fact that the spectrum has an edge, that would also requires exponential long time.
Yeah, if you want to probe the edge, You can see that you're approaching something that looks like the edge, but if you want to probe the edge, then you need exponentially long times in the entropy. Yeah, that's at the end of the day, that's like probing the ramp and the plateau. For this, you need exponentially light times. That's essentially the same thing. If you're probing the granularity of
going from exponential to power law decay.
Yeah.
It's before getting to
Yes.
Raman,
Yes. Yes. So you have first the exponential decay, then you have power law. So this is the regime that I'm probing, the one where I have the power law decay. Then you have the ramp and the plateau.
No. Power law is actually, how long do I need to wait to get to power law? It's just
page time, more or less. Yeah.
Okay, so
Kind of. Yeah.
So even if I could also measure correlation function.
Yes.
And see the deviation.
Yes. Okay. Yes. I mean, that's essentially, another way of saying what I'm proposing.
So in case of spinning the cones,
yes.
Do you expect qualitatively the same transparency features?
So it's going to be a little more complicated because the black hole is already spinning. I think that the transparency gap is going to be smaller because the relative increase in entropies or in energy is going to be smaller. But I think that there should be, the energy levels are still going to be quantized. When you're going to have that, I think that the gap is going to be smaller, but I think it should be there. So it shouldn't be, it's a 5-10 minutes calculation to do that, but I haven't done that, or at least to estimate the gap.